In this video, we will look at the energy of electrons in a material with a periodic atomic structure. Most semiconductor materials, such as silicon, have periodic atomic structure. We call it a crystalline structure. By following a simplified quantum mechanical approach, we will show that the energy of electrons in semiconductors is grouped in bands. This video aims to understand the origins and the importance of electron energy bands for semiconductors. Specifically, we demonstrate how we visualize these energy levels in so-called energy band diagrams. Understanding band diagrams is of utmost importance for solar cell engineers. In the previous video, it was described how atoms bond together to form a solid material. Now we will take a look at the energy of electrons in a regular atomic structure. This first part of the video will essentially serve as a derivation for energy band and dispersion diagrams. For this course, you do not need to follow all the complex physics here, and you can skip it. You can go ahead to the diagrams themselves that are discussed later in this video. However, for those of you who want to dig deep into the physical understanding of these diagrams, we will explain the presence of the bands of energy levels of electrons in a solid starting from the energy of an electron. Since the quantum mechanical approach to determine the energy of an electron in a real solid is rather complex, we will start by making some simplifying assumptions. Let's consider a case in which the lattice structure is perfect and all the atoms are fixed in one position. Let's then consider a one-dimensional crystal lattice as shown in the slide, with the lattice constant equal to A and composed of n atoms. In quantum mechanics, the Schrödinger equation relates the energy of a particle to its wave function. This differential equation is of the second order, and you can see it presented here in the slide. As you can expect, solving the Schrödinger equation for a real three-dimensional case is mathematically complex. Therefore, we will use models and simplifications that will allow us to derive the energy of an electron in a simpler one-dimensional lattice structure. This diagram shows the potential energy experienced by an electron crossing one-dimensional lattice. When considering only Coulombic forces as a result of atom core electron interactions, the resulting potential energy function, U of x, will be periodic as shown in this slide. It is important to remark that electron-electron interactions within atoms are neglected, since their average contribution to the potential energy is almost zero. When dealing with a periodic function, we can apply an additional approximation, the Bloch theorem. As a result, we can solve the Schrödinger equation focusing only on a single unit cell. We assume that the lattice is built up of a number of unit cells and consider the other unit cells to be equivalent. In this equation, you can see that the wave function in a certain position of the lattice is dependent on the lattice constant A and a new parameter, k, which is called the wave number. It is important to define k in order to determine the allowed energy states for an electron in a periodic lattice. The assumption of a one-dimensional periodic system enables us to arrive to the following conclusions. It can be shown that for a one-dimensional system there can be only two values of k for each allowed energy state. Besides, the values of k are periodic, and they repeat every 2 pi over a, that is the lattice constant. Moreover, if we apply periodic boundary conditions in a finite crystal lattice, k has a distinct number of values. This number equals the number of units, or in our case, atoms, that form the lattice. Let's assume the number of atoms is capital N. Since k is inversely proportional to the lattice constant, it can be concluded that the closer the atoms are to each other, the closer the k values will be spaced. And this can lead to a quasi-continuous range of allowed k values. The periodic potential energy can be further idealized according to the Kronig-Penney model. The periodic potential energy is represented by a bearer denoted as U and a well. The energy of the well is set to be 0. The bearer and the well that describe the periodic potential energy function form a unit cell. We define the dimensions of the unit cell by -b and +a as boundaries along the x-axis. If we apply the boundary conditions within such unit cell, we can solve the Schrödinger equation. The resulting solution includes the parameters alpha and beta, which are related to the energies in specific regions of the potential energy function. From this solution, we can see that each value of k corresponds to a specific energy. Besides, to satisfy the relationship, the cosine of k times a plus b must assume a value in the range between -1 and +1. In order to visualize the results, let's now define Xi as the ratio between the particle energy E and the maximum potential energy U0. The allowed energy values for the system are then those that satisfy the equation we saw in the previous slide. If we adapt this equation using the newly defined components of Xi and alpha 0, we can show that allowed solutions lie in the range between -1 and +1. And if we plot the adapted equation as function of Xi, we can observe that it is an oscillatory function. The regions where the function have values between -1 and +1 are enclosed in the blue boxes. These boxes represent the sets of allowed energy states that the system, our one-dimensional lattice, can have. These ranges of allowed energy states for electrons are what we call energy bands, while the spaces in between are forbidden energy states for electrons. But why are we interested in wave numbers and energy bands? To understand it, we will now look at the energy dispersion diagrams. An energy dispersion diagram, also referred to as EK diagram, relates the electron energy states to the wave number k. Doing so, in a one-dimensional system, we are able to know the energy of an electron for any specific value of k. But not only that. The wave number is also related to the particle momentum. In classical mechanics, it is defined as the product of the mass of an object and its velocity. This resulting vector plays an important role in the mechanisms and energetics of energy transitions in a semiconductor. We can extend our analysis to a three-dimensional system. In this case, we refer to k as a wave vector, and it depends on the crystal orientation that has to be taken into account. However, if we do so, the resulting plot will be very complex and difficult to analyze. For this reason, generally, only the regions that are the most likely to be occupied by electrons are plotted. Moreover, due to the symmetry of crystals, we can choose to plot only the positive values of k. It is important to realize that these energy levels vary depending on the orientation that is taken into account. This means that if we look at an electron in a crystal lattice, it will be able to propagate differently in different directions. Here, you can see how the dispersion diagram looks like for silicon crystal. As you saw, we can use dispersion diagrams to extrapolate accurate information regarding the energy of an electron. However, due to their complexity, these diagrams are not commonly applied to describe the working principle of solar cells. Instead, we used the so-called energy band diagrams to represent energy behavior of electrons in semiconductor materials and solar cells. When discussing three-dimensional dispersion diagrams, we said that only the bands that are most likely to be filled with electrons are represented. For device operation, valence electrons are of the utmost importance, and therefore we focus on the energy of valence electrons. The allowed energy levels of valence electrons form the so-called valence and conduction bands. The valence band comprises the energy levels of all valence electrons in a semiconductor material at absolute zero. These electrons are the ones making the covalent bonds, and when forming a bond, they are immobile. So electrons occupying energy states in the valence band are fixed in the lattice and cannot move around. However, When we supply the extra energy, for example in the form of heat, they can be excited and leave the bond. When this happens, they gain energy and fill available energy levels in the conduction band. In semiconductors, electrons with energies in the conduction band are mobile and can move throughout the material, allowing the material to conduct electricity. In the case of solar cells, as we will see in the following videos, light can excite valence electrons to the energy levels of conduction band. This is the first step to convert energy of light directly into electricity. The difference between conduction and valence band is known as the band gap. There are no energy states available for electrons between the top of the valence band and the bottom of the conduction band. So, with these three definitions in mind, let's take a look at what a band diagram looks like. Here in the figure, energy is represented by the y-axis. The valence band is given in blue and the conduction band in yellow. There are numerous energy states in both bands, but we will mostly be concerned with the edges of these bands. These parts of the bands are the most important parts for understanding photovoltaic applications. We can usually draw the bands like this, with a solid yellow box for the conduction band and a solid blue box for the valence band. We can also define the band gap, which we denote as Eg, as the difference between the bottom edge of the conduction band, Ec, and the top edge of the valence band, which we denote Ev. We will use this diagram over and over again throughout this video series. And as I said before, it is enough for you to just understand that electrons occupying energy levels in the valence band are immobile. When they are excited to the energy levels of the conduction band, they become mobile in a material. However, if you want a deeper explanation for what these bands actually mean, you can always refer to this video. Now that we have defined the energy bands, we need to make an important distinction between the different types of semiconductor materials. This brings us to the concepts of direct and indirect bandgap materials. The distinction depends on the relative position of the energy bands in the dispersion diagram. We call a material a direct bandgap material when the maximum energy level of the valence band aligns vertically with the minimum energy level of the conduction band. This means they occur at the same value of the wave number k. On the other hand, for indirect bandgap materials, the highest point of the valence band is not aligned with the lowest point of the conduction band. The band edges are shifted relative to each other in k-space. But why is this alignment so important for solar cells? To answer that, let's look at the electron excitation process in both cases. In a direct bandgap material illustrated to the left, an electron can be excited from the valence band to the conduction band simply by absorbing a photon with energy equal to or greater than the bandgap. The momentum of a photon is negligible, so the electron's momentum essentially stays the same during this vertical transition. However, the situation is different for an indirect bandgap material shown on the right. Because the band edges are misaligned, the electron must change its momentum significantly to reach the minimum of the conduction band. A photon cannot provide this momentum change alone. Therefore, the transition requires the assistance of a phonon, which is a lattice vibration. The interaction involves both a photon to provide the energy and a phonon to provide the required momentum shift. Silicon, the most common material for solar cells, is an indirect bandgap material. This makes the absorption process slightly less efficient compared to direct bandgap materials, which is why silicon solar cells require thicker wafers to absorb sunlight effectively. In this video, we have presented the fundamental equations used to solve the electron energy bands. These include the Schrödinger equation, the simplification provided by the Bloch theorem, and the specific solutions for the Kronig-Penney model, which allow us to mathematically determine the allowed energy states. Finally, we described why the absorption process in indirect bandgap semiconductors is slightly less efficient compared to that in direct bandgap materials.